In this session, we'll discuss few questions from microwave engineering. First question is a lossless line of 50 ohms is terminated in a load of 100 ohms. The VSWR is. VSWR stands for voltage standing wave ratio. VSWR is given by 1 plus mod tau by 1 minus mod tau, where tau is reflection coefficient. Tau equal to ZL minus Z0 by ZL plus Z0, where ZL is load impedance. In this case, load impedance is 100 ohms and Z0, characteristic impedance of the transmission line, is 50 ohm. Therefore, reflection coefficient tau equal to 100 minus 50 by 100 plus 50. Answer is 50 by 150, or it is given by 1 by 3. Reflection coefficient tau equal to 1 by 3. So, VSWR equal to 1 plus 1 by 3 divided by 1 minus 1 by. Answer is 4 by 3 divided by 2 by 3, 2. So, correct answer is option B. In this question, the characteristic impedance of a coaxial cable is proportional to. The characteristic impedance of a coaxial cable is proportional to. Coaxial cable is having inner diameter D1 and outer diameter, that is D2. Outer diameter is D2. Characteristic impedance of the line Z0 equal to 138 divided by square root of epsilon r into log D2 by D1, where epsilon r is the dielectric constant of the medium between the two conductors, outer and inner conductor. Dielectric constant. D2 is outer diameter and D1 is inner diameter. So the correct option is Z0 will be proportional to log D2 by D1. The correct option is option 4. That is logarithm of the ratio of outer and inner diameter of the cable. This is a question asked for Kerala PSC 2009. It is required to match a 73 ohm load to 600 ohm feeder line. What must be the characteristic impedance of the quarter wave transformer used directly? It is used directly connected to the load. Characteristic impedance of a quarter wave transformer. Theory of quarter wave transformer that connects load impedance ZL with a transmission line having characteristic impedance Z0. If we are using a quarter wave transformer to connect transformer having length lambda by 4 to connect the line with the characteristic impedance Z0 to a load impedance with the load impedance ZL, then the characteristic impedance of quarter wave transformer Z0 dash equal to geometric mean of characteristic impedance of the line and load impedance ZL. So in this case, characteristic impedance of the line is 600 ohms and the load impedance is 73 ohms. The answer is geometric mean of 673, that is equal to 209 ohms. The correct option is option C. In this question, the resistance circle in the outer perimeter of Smith's chart represent a resistance value of. The equation of constant R circles in a Smith's chart is tau R minus R by 1 plus R whole square plus tau I square equal to 1 by 1 plus R the whole square. And this represent constant R circles in Smith's chart, where tau R is real part of reflection coefficient tau and tau I the imaginary part of tau. That is, tau is a complex quantity, tau R plus J into tau I. Now, R is normalized resistance, normalized load resistance. That is, ZL by Z0 can be written as R plus JX. So, R is a real part of normalized impedance and is called normalized resistance. Here, the radius of R circle is 1 by 1 plus R. So, when R equal to 0, radius equal to 1. When R equal to 0, radius is 1. When R become infinity, radius become 0. In this question, We have to find the resistance value corresponding to circle of radius equal to unity. That is, correct option is R equal to 0. If radius is 0, then R equal to infinity. The longest free space wavelength that can be propagated in a parallel plane waveguide is nearly equal to. If we consider a guided wave between two conductors having a separation equal to A, the wavelength, maximum wavelength lambda c equal to 2A. So the correct option is the maximum free space wavelength that can be propagated in parallel plane waveguide is twice the wall separation. In this question, a rectangular waveguide with the dimensions 3 cm and 1.5 cm. This waveguide is a rectangular waveguide. This is 3 cm and this is 1.5 cm. Have a rectangular waveguide. We have to find the cutoff frequency for T10 mode. The expression for cutoff frequency Fc equal to C by 2 into square root of m by a whole square plus n by b whole square. For T10 mode, m equal to 1, n equal to 0, therefore Fc will be equal to C by 2 into m by a. C is velocity of light in free space, that is 3 into 10 raised to 8 meter per second. A equal to 3 centimeter, the longer dimension, that is 3 into 10 raised to minus 2. Substituting, we will get 3 into 10 raised to 8 by 2 into m is 1 by 3 into 10 raised to minus 2. So the answer will be 5 gigahertz. The correct option is option D, that is 5 gigahertz. So in this question, VSWR is given. We had to find the reflection coefficient. VSWR, voltage standing wave ratio, that is S equal to 1 plus mod tau by 1 minus mod tau. Tau is a real value. Mod tau simply equal to tau. So S equal to 1 plus tau by 1 minus tau. From this formula, we can calculate the reflection coefficient tau as S minus 1 by S plus 1. And substitute for S. S is 3. 3 minus 1 by 3 plus 1. That is 2 by 4 equal to 1 by 2. So reflection coefficient is 1 by 2. In this question, the distance of 20 kilometer from a point source, the power density is 100 micrometer square. What is the power density in microwatt per meter square at a 10 kilometer? Power density is power radiated per unit area. Power radiated per unit area, that is power density, S is PR by area. For PR is radiated power. This is radiated power. PR is radiated power. PR divided by 4 pi r square. Area in a spherical wavefront, area is 4 pi r square. This area equal to 4 pi r square. Since radiated power is a constant, so S into r square equal to PR by 4 pi. This quantity is a constant value. Therefore, S1 R1 square equal to S2 R2 square. Now we have to find the distance where power density at 10 kilometer. So we will take S2. S2 equal to S1 R1 square by R2 square. S1 is our power density at 20 kilometer, that is equal to 100 microwatt per meter square into 20 square by 10 square. Answer is 400 microwatt per meter square. Correct option is option D. The signal in UHF range normally propagates. There are different propagation means for EM wave. UHF signals are normally propagated as space waves or line of sight propagation. Other modes of propagation are ground waves and sky waves or ionospheric propagation. Here we have a question from a radar range. If in a radar transmitter, the peak transmitted power is increased by a factor of 16, the maximum range will be increased by. The radar range equation is radar range R equal to Pt into Gt into Gr lambda square sigma by 4 pi whole cube S minimum whole to the power of 1 by 4, where Pt is transmitted power. Pt is transmitted power. Gt transmit antenna gain. Gr receive antenna gain. Lambda wavelength of signal. Sigma radar cross section. S minimum is the minimum detectable signal. Radar range equation give a range that is proportional to transmitted power raised to 1 by 4. Since range is proportional to Pt raised to 1 by 4, if Pt increases by a factor of 16, then the range will be increased by a factor of 16 raised to 1 by 4, that is equal to range will be increased by a factor of. The correct option is option D. This question is a Kerala PSC question asked in 2009. An antenna has 40 ohm antenna resistance and 60 ohm radiation resistance. The efficiency of the antenna. The efficiency of antenna depends on the radiation resistance and loss resistance of the antenna, and is given by RR by RR, that is radiation resistance plus loss resistance RL, where RR is radiation resistance, and this resistance is responsible for power radiated by the antenna. Radiation resistance, here it is given as RR is given as 60 ohm, and RL, that is loss resistance of antenna loss resistance, loss in the conduction and dielectric material, loss resistance is RL equal to 40 ohms. So efficiency of antenna, radiation efficiency of antenna is 60 divided by 60 plus 40, so 60 by 100. As a percentage, we may write 60%. Answer is 60%. The correct option is option D. Radiation resistance of lambda by 2 antenna. Lambda by 2 antenna means half wave dipole antenna. Half wave dipole antenna. Radiation resistance for half wave dipole antenna is 73 ohms. Radiation resistance is 73 ohms. Correct option is option C. Here we have a question in AM system. An AM transistor has an RMS antenna current of 11 ampere when unmodulated. So RMS current when unmodulated, that corresponds to IC equal to 11 ampere. This corresponds to carrier current, RMS carrier current. When and 13 ampere when sinusoidally modulated, IAM modulated RMS current. Modulated RMS current is IAM equal to 13 ampere. Using these two currents, we can calculate corresponding power. Power of carrier is IC square into RL. Some power that is dissipated in load resistance RL will be IC square into RL. Similarly, PAM will be equal to IAM, RMS value of current square into RL. So PAM by PC equal to IAM square by IC square. We know that power of AM signal is PC into 1 plus M squared by 2. So this is expression for power of AM system. Therefore, PAM by PC equal to 1 plus M squared by 2, so which is given as 13 square by 11 square equal to 1 plus M squared by 2. Is 169 by 121 equal to 1 plus M squared by 2. We can calculate M squared by 2 as M squared by 2 will be 148 by 121. So M will be equal to 0.79. So the correct option is option A, 0.79. In this question, feature of strip line is asked. Strip line is a antenna. The geometry of micro strip line consists of a dielectric slab having very small thickness D. Thickness of dielectric slab is D, having a complete metallization. So this face is completely metallized, so coated with a metal metal on the one of its surface and a metal patch on the other side. So here we have a metal patch, maybe arbitrary shape. Here we are drawing a rectangular shape. This is a metal patch, and feeding for the antenna is done between the metal patch and the metal surface. The metal patch is the front surface, have various shapes. The features of microstrip lines are, it is a planar type of transmission line, that is correct. It is a semiconductor device, it's not a semiconductor device. It is used in conjunction with a semiconductor microwave device, that is correct. Can support TEM wave, also correct. The correct option is, it is a semiconductor device. This question, the length of the antenna is given as lambda. Antenna has a length lambda, so lambda is the length of antenna. The radiation pattern will be like this. So the maximum radiation occurs at the right angles to the antenna. This is direction of maximum radiation. So correct option is, radiation at right angles is maximum. This is option B. Next question, a Yagi antenna in a horizontal plane produces, option A, broadside pattern, B, end-fire pattern, C, a figure of 8 pattern, D, none of the above. We have Yagi antenna with one feed element or driven element and several parasites, and this is reflector having length more than the driven element, and other parasites have length less than the driven element. This is driven element, and these are directors. So the field pattern will be end-fire. So maximum radiation will occur in this direction. So it is an end-fire pattern. When an antenna is placed in a vertical plane, it will produce, if a vertical antenna is placed, it will produce vertical polarization. So electric field will be in vertical plane. E field will be in vertical plane, so the wave is vertically polarized. If we use a horizontal antenna, electric field will be horizontally polarized. Circular polarization is sometimes used for satellite radio communication to overcome the effect of propagation anomalies and the effect of fading. So correct option is vertically polarized wave, that is option D. This question is related to the working of traveling wave tube. Traveling wave tube, or TWT, is a microwave amplifier used to amplify RF signal in microwave frequency range. TWT is a slow wave structure. In TWT, interaction between electron beam and RF field takes place when the velocity of electric field or axial component of RF field become comparable to the velocity of electron. The phase velocity component of RF field is kept at a slightly lower value so that energy transfers from electron beam to boost the RF signal. Then the kinetic energy of electron decreases as they reach the collector. The correct option is the RF the phase velocity of axial component of the field of a slow wave structure is kept slightly less than the velocity of electron. Option A is the correct option. Here we have a question asked for Kerala PSC 2009. The refractive indices of the core and cladding of an optical fibre are 1.55 and 1.51. What is the critical angle of incidence? This is a typical question from optical communication. Here the refractive index of core, that is N1, is given as 1.55 and the refractive index of cladding N2 is given as 1.51. We have to find the critical angle. Now what is critical angle? Critical angle is the minimum angle required for the total internal reflection. When light enters from a denser medium to rarer medium, this is denser medium like core in an optical fiber, denser medium to rarer medium. Denser medium is having refractive index N1 and the rarer medium is having refractive index N2. If the angle is equal to critical angle theta c, then the light will just start to reflect into the denser medium, and this angle will be 90 degree. By Snell's law, n1 sine theta c equal to n2, this angle of refraction is 90 degree, so sine 90, so n1 sine theta c will be equal to n2, sine 90 is 1 into 1, therefore sine theta c equal to n2 by n1, where n2 is the refractive index of rarer medium and n1 is the refractive index of the denser medium. So theta c equal to sine inverse n2 by n1. Okay, now we can calculate theta c. In this case, theta c will be equal to sine inverse 1.51. This is refractive index of rarer medium divided by refractive index of denser medium is 1.55. The answer is 76.95. Okay, so it is calculated. Theta c, critical angle theta c is calculated using the formula sine inverse refractive index of rarer medium divided by refractive index of denser medium. Here we have another question which cannot be a part of optical communication system. We know that avalanche photodiode, LED, semiconductor laser, all these three devices are optoelectronic devices and they are used in optical communication system. Avalanche photodiode is a photodetector. LED and semiconductor laser are used as optical source in optical communication system. Now gun diode is a microwave device that has no role in optical fiber communication. So correct option is gun diode. This is a question asked in Kerala PSC 2017. Total internal reflection can take place when light travels from, options are air to glass, C, rarer to denser medium, option B is glass to air, and option D, denser to rarer medium. We have already discussed that total internal reflection takes place when light travels from denser to rarer medium. So there are two options that are correct. Option B is glass to air. Here glass is denser medium and air is rarer medium. But more general answer for this question is option D. So correct option is option D. Here we have a question. It asks the structure of optical fiber. The structure of optical fiber consists of multimode step index, single mode step index, graded index. So the structure of optical fiber consists of, one type of optical fiber is single mode. In single mode, the light propagates in a single or fundamental mode in the core. It allows a single light path and typically used in laser signaling. It has very small in size. It has core of approximately 5 to 10 micrometer in diameter. So the core diameter is very small, so it can support only one mode of propagation, that is direct mode. The light can travel directly from source to destination. This type of fiber is called single mode fiber. Second category of fiber is multimode fiber. In multimode fiber, it again divided into two, step indexed and graded indexed multimode fiber. Correct option for this question is all the above.